Welcome to section 5.1. We're going to be learning about composite functions. Essentially, a composite function is when we plug a value into a function, and then whatever we get, we plug that into another function. So on a mapping, it would look something like this. We would have our domain of all of our x values, and then we'd have a mapping into the range. So I'll just call it x, something generic. And then let's say our function f would take x to f of x. And then we would have another function g that would take f of x and map it in to the range of g. And so really it would be g of that value f of x. Okay, and then we can also demonstrate this with a table. So for instance, let's say we're looking at 3. X equals 3, and then we'll apply a function g, and it's going to go to 21. And so now g of 3 is 21, and then if we apply f to that, we would get -9. All right, so our process is we go x to g of x to f of g of x. And so in this case, that looked like 3, and then we looked at g of 3, and then we looked at f of g of 3. All right, and then all with numbers, if you look at our table, we went 3, g of 3 is 21, and then we took 21, f of 21 is -9. Okay, so what we did this process, we apply a function and then apply a function again, is called a composite function. So let's move on down to our definition. If f and g are functions, x is in the domain of g and g of x is in the domain of f, then we can form the composite function f of g. All right, so that's what we did up here. We're just using a new notation, and the new notation is this open circle right here. So the definition we're doing is when we have this open circle, that's a composite function, and the definition is, it is f of g of x. All right, so that's exactly what we did above. F of g of x, that was right here. All right, and then I also wanted to point out some other things. X has to be in the domain of g, right? So 3 was in the domain of g. Those are all your x values. And then g of x, this 21, g of x has to be in the domain of f. All right, so that's this part in here. X is in the domain of g, and g of x is in the domain of f. Let's practice again. We're going to actually find not f of g of 3, because we just found that. F of g of 3 was what we did above. And we said that was -9. So let's find f of g of 4. All right, so take a couple seconds, see if you can figure it out. How I like to do it, first things first, I like to write out the definition So where do we plug in what to what? So when we write it according to definition, just like we see it left to right, is how we write it. So we go f of g of 4. So f of g of 4. So we work from the inside out. So we start with x equals 4, and we plug it into g. So let's figure out what g of 4 is first. So x equals 4, and we plug it into g. So x is 4, g of 4 is 23. So let's write that out. G of 4 is 23. And now over yonder, the other table, this is our f function. So we're going to find x equals 23, that's the inside stuff. And we apply f of 23, it's negative 15. So our answer is negative 15. Okay, let's do something similar now with a graph. So use the graphs below and find f of g of 1, or f composed with g of 1. So again, first step, I always like to write out the definition. So it means we take x equals 1, and we applied our g function, and then whatever that is, we plug it into f. So let's start with x equals 1 and find g of 1. All right, so this is our g line. And x equals 1 on our graph of g of 1 is negative 2. So let's write that. This is going to be f of negative 2, because g of 1 is negative 2. Okay, so now the red line is our f function, and we're going to apply negative 2. So when x is negative 2, on our red line, that's going to be negative 4. So our whole answer is negative 4. Okay, so we make these substitutions. So again, we start at x equals 1, g of 1, here's x equals 1. On the blue line, g of 1 is negative 2. So we substitute g of 1 with negative 2. F of negative 2, so when x is negative 2, on our red line, f of negative 2 is negative 4. So the whole answer is negative 4. Okay, so we're going to be working a lot with equations and composite functions. So we're going to compose functions when they're written as equations. So we have two given functions, f and g. We want to find f of g, or f composed with g of 2. So just as before, a nice first step is to write out that definition. So f of g of 2. All right, so again, we work from the inside out. So we start with x equals 2, and we're going to find g of 2. We're going to plug in 2 into our g function. All right, so we can do that a couple different ways. We can do side work, or we can plug it in directly. So we have two options. We can calculate g of 2 on the outside, or g of x is 5 minus 4x. We can write 5 minus 4 times 2. So we're plugging in two things. All right, or alternatively, we could do it off to the side. So g of 2 is 5 minus 4x, but x is 2. All right, however you slice it, g of 2 is 5 minus 8, or negative 3. So we are going to look at f of negative 3. And f of x is negative x plus 6. So there's lots of negative numbers. Let's make sure we use our parentheses. So negative x plus 6, but x in this case is negative 3. So this right here is saying the opposite of negative 3. Minus minus becomes positive. So this will be positive 3 plus 6 The answer is 9. All right. So f composed with g of 2 is 9. We're going to do the same thing, but we're going to do it opposite. So now we're going to go g of f of 2. So now we're going to take the 2 and we're going to plug it into the f function first. And again, you can do this two ways. You can plug in the whole function at 2. You can do a little scratch work. I'll do a little scratch work off to the side. F of 2, I'll do it down here. F of 2 is the opposite of 2 plus 6, since it's the opposite of x plus 6. So f of 2 is 4. So this is asking us to evaluate g of 4. And g is 5 minus 4x. And x is 4. So 5 minus 16. And 5 minus 16 is negative 11. 5 minus 16 is negative 11. Okay, so what this brings up, a good point. Whoops, sorry, 5 minus. It brings up the fact that f of, there it goes, g of 2 is 9. And g of f of 2 is negative 11. So we have this word commutative property. Addition and multiplication is commutative. It means the terms can commute. We can interchange them. But in this case, that's not true. So with composite function, it's not commutative. Okay. Moving on. Go ahead and try this example on your own. Try A and B together, or excuse me, on your own. So go ahead and push pause, and then come back and see your solution, and we'll do C and D together. All right, so let's look at your solutions. They're in red. First thing you guys did was translate f of g of 3 by definition. You evaluated g of 3 to be 2. So then you plugged in 2 into f. You got negative 1. Same thing with this next part, g of f of 3. You evaluated f of 3 to be 2. So you plugged in g of 2 and you got 0. And again, we see that we cannot interchange f and g because f of g of 3 is negative 1, g of f of 3 is 0. All right, now we're going to find an equation of f of g. And we're going to start off the same way. We're going to start off by writing what f of g of x would be. So that's what it means when we're finding an equation. So for any value of x, not just particular values, we're going to find the equation. And in this case, f composed with g, we're going to plug in g into f. So our g function is 2x minus 4. So in our f function, wherever we see an x, we're going to plug in 2x minus 4. All right, so f is, and I'm going to write it up here, 3 times x minus 7. And again, x we're saying is 2x minus 4. That's the input. Okay, so let's simplify this always. Always simplify to get full credit. That means no parentheses, so we're going to distribute the 3. So 6x minus 12 minus 7. And then combine your like terms. So the equation of f of g of x is going to be 6x minus 19. And there you go. And notice if we plugged in, let's go back to part A, if we were to plug in 3, Well, 6 times 3 is 18, minus 19 is negative 1. And that's exactly what we got in part A. If we were to actually plug in the 3, we would also get negative 1. 6 times 3 is 18. 18 minus 19 is this negative 1. All right, go ahead and push pause, and you guys are going to find an equation of g of f. All right, so you guys plugged in f into g this time. F is that 3x minus 7. And then g is 2x minus 4. The input, though, is 3x minus 7. So you distributed and you combined like terms to get your g of f equation. And again, notice if we go back to part B, when we plugged in 3, if we were to plug in 3, we would get 6 times 3 is 18. 18 minus 18 is 0. So g of x of 3 is still 0. And that's exactly what we got from part B. Okay, let's take a look at our next example. Sometimes we have to work backwards. So we're going to consider this function 5x minus 2 squared, and we're going to pretend that this is a composite function, such that f of g of x is h of x. All right, so let's look at h of x. And when I'm looking at h of x, I'm noticing two things. I'm noticing we have a function inside parentheses, and I'm noticing we're squaring that function. So I would consider the stuff inside the parentheses to be one function that we're plugging into a square function. All right, so f of g of x, so g of x is what we're plugging in to into another function. So like the inside function, if you will, is something like 5x minus 2. And then what we're plugging that into, you figure we take the input and we square it. So we take the input and we square it. That's the same as x squared. All right, and again, we could check our work. Always check your work. F composed with g. So again, we want to know, does this equal our h? We call g 5x minus 2. And then f is the input squared. So we would take our input and square it. And does that get us back to h? Yes. So this would be an example of two functions composed give us h of x.